Let's be real, the internet is a completely chaotic environment. I mean, think about it. Billions of devices are firing unfathomable amounts of data into the digital void every single second, bouncing all over global infrastructure. So how does it not all just fall apart? Well, welcome to this explainer. Today, we're unpacking the invisible engine that keeps our digital lives running smoothly. We're talking about the unsung hero that mathematically ensures your data gets exactly where it needs to go every single time.
Okay, let's dive into this. Here is our roadmap for today. We're going to start with the internet's unsung hero. Then we'll break down the mechanics of reliability. After that, we'll explore TCP in your daily life. And finally, we'll weigh the cost of perfection.
All right, first up, the internet's unsung hero. Before we really get into the nuts and bolts, we need to understand the stakes here. Launching delicate data into that chaotic global storm we just talked about, that requires a serious, rigorous protector. Enter the Transmission Control Protocol, or a TCP. Think of the baseline internet protocol, IP, as your regular postal service. It routes the mail, sure, but it makes absolutely no promises about delivery. TCP, on the other hand, is like the highly organized certified mail department of that IP suite. It provides reliable, connection-oriented communication. Basically, it mathematically ensures your data arrives perfectly intact and in the exact right order.
Moving right along to part 2, the mechanics of reliability.
So, what mechanical features actually act as this magical shield for our data? Well, TCP achieves its legendary reliability by being strictly connection-oriented. It flat out refuses to just shout data into the void hoping someone hears it. Step 1 is establishing a formal connection. It's like a precise digital handshake between the sender and the receiver. Only after that handshake is completely confirmed do we move to step 2, which is transmitting the data in a precise, agreed-upon sequence. And finally, step 3 gracefully terminates the connection, making sure absolutely no data is left hanging or incomplete.
Now, during that transmission phase, TCP is working overtime to guarantee delivery. It uses this really strict system of acknowledgements. If the receiving machine doesn't send back a very specific "got it" message, TCP automatically retransmits the missing packets, no questions asked. It also features robust error checking, using complex mathematical checksums to verify data integrity. It's like having a certified quality inspector on the line. Any corrupted packets are instantly discarded and replaced. Oh, and it manages all of this in full duplex, safely handling two-way traffic simultaneously without dropping a single beat.
Now, what's really interesting about this slide is how easily people confuse flow control and congestion control. But the distinction is absolutely crucial for network stability. Flow control protects the specific device you're communicating with. It paces the data so a blazing fast sender doesn't completely overwhelm a slower receiver. Congestion control, on the flip side, protects the network infrastructure itself. It actively throttles your transmission rate based on broader network traffic to prevent wide-scale data jams. Honestly, it's a highly intelligent, self-regulating ecosystem. Let's bring this closer to home with Section 3, TCP in your daily life.
Let's pivot from theory to reality, because whether you realize it or not, you rely on this invisible engine constantly. Think about loading a secure web page via HTTPS or pulling down your inbox with IMAP. Those require flawless data delivery, which is exactly why they run on TCP. When you transfer files over FTP or secure a remote terminal with SSH, a single dropped packet could literally corrupt an entire file or sever a vital command line. It is the unbreakable foundation for heavy-lifting database queries in MySQL and PostgreSQL, and it even operates behind the scenes in your VoIP calls and online gaming, reliably setting up the SIP sessions and ensuring your chat messages actually arrive where they're supposed to.
Which brings us to our final section, the cost of perfection. You know, in cloud computing and networking, every robust feature comes with a strategic trade-off. We know TCP is practically bulletproof, but here's a question for you. Is perfect reliability always the best choice? Does every single application across the internet actually need perfectly ordered delivery? To truly grasp network architecture, we have to recognize when TCP's heavy-duty mechanics are exactly the right tool for the job and when they might actually hold a system back.
So, the crucial point is that TCP is strictly chosen for scenarios where ensuring every piece of data arrives flawlessly is vastly more critical than raw speed or minimizing latency. Think about it. If you're downloading a bank statement, you absolutely cannot afford a missing zero just because the network wanted to move a little faster. Accuracy is paramount. But the trade-off for all those acknowledgements, digital handshakes, and strict error checks is time. TCP willingly sacrifices instantaneous speed to guarantee absolute mathematical perfection.
As the saying goes, TCP is chosen for applications where data integrity and reliability are crucial. It truly is the bedrock of a trustworthy internet. But this leaves us with a pretty fascinating question to chew on. As our modern applications demand increasingly instantaneous real-time speeds for things like live video streaming and cloud gaming, will the hidden architecture of the web continue to value perfect accuracy above all else? Or are we going to see a massive shift toward faster, riskier protocols? Next time you load a secure web page or download a critical file, take a second to appreciate the invisible engine working overtime to keep your data intact. Thanks for joining me for this explainer.